Okay, so picture this. You're on a plane, it's late at night, and you're flying over a huge city.
Yeah, you see that whole grid of glowing lights, the flow of traffic.
Exactly, it's mesmerizing. But what you're actually looking at, it's a giant living math problem.
That is the perfect way to start. We're looking at the world through the lens of, well, the graph.
And we're not talking about a bar chart here.
No, not at all. This is the fundamental data structure that models relationships, from those city streets to the actual pathways in your brain.
It's like the skeleton of connectivity. So in this model, the intersections are nodes.
Nodes, right, and the roads connecting them are the edges.
And this is different from something like a tree structure, which is really clean and hierarchical, like a file system.
That's the key difference. A tree is strict. It has one root, and it never, ever has loops.
You can't go down one branch and magically pop up somewhere else.
Exactly. But a graph embraces the chaos. It's full of cycles. You can have 1,000 different ways to get to the same spot.
And that's where it gets complicated. Figuring out which of those 1,000 paths is the best one.
Which is where the search begins.
So if I'm a computer trying to navigate this, I have, what, two main ways of thinking? I can be cautious or I can be...
Aggressive, yeah.
Right, aggressive.
So on one hand, you have breadth-first search, or BFS. Think of it like dropping a stone in a pond.
The ripples expand out layer by layer.
Exactly. It checks every single one of its neighbors before moving out to the next layer. It's very thorough, and it'll find the shortest path.
But it must use up a ton of memory, keeping track of that whole expanding circle.
It does, which is why you have the other approach, depth-first search, DFS.
The lightning bolt strategy.
That's it. You just pick a path and you dive as deep as you can until you hit a wall. Then you backtrack and try another deep path.
It's much lighter on memory, I'd imagine, but you could end up going down a really long, useless path when the answer was right next to where you started.
Precisely. But here's the huge catch with both of those strategies.
What's that?
Neither one of them thinks about cost. And in the real world, not all roads are created equal.
Right. Some have traffic, some have tolls. They're weighted.
Which brings us to the grandfather of all this, Dijkstra's algorithm.
This is what's running in your phone's GPS. It's not just counting stops, it's calculating the total cumulative weight or cost to guarantee the most efficient route.
The problem is, Dijkstra is a bit of a perfectionist. It explores everything. If you're going from New York to LA, it might waste time checking routes to Boston.
So that's why we have A or A star.
A star is smarter. It adds a bit of intuition. The formula is basically your history, the actual cost to get where you are, plus a heuristic.
And a heuristic is just an educated guess.
An educated guess of how much farther you have to go. It's like a magnetic pull, a beam, that focuses the search toward the goal and tells it to ignore the obviously wrong directions.
So it's a balance of accuracy and speed, but even A star has its limits.
Oh yeah. You eventually hit a wall, you hit problems that are just too complex.
The NP hard problems. The classic example is the traveling salesman.
Right. Visit 50 cities only once, find the shortest route. The number of possibilities is so huge you just can't brute force it. The sun would explode before your computer finished.
So we have to give up on being perfect.
We trade perfection for a good enough approximation. And to do that, we can, look to nature.
Swarm intelligence. We look at ants.
A single ant is, well, pretty simple. But the colony is a genius. They leave pheromone trails.
The shorter a path is, the more ants use it, the stronger the trail gets. It's like a positive feedback loop that finds the best route.
It's a process called stigmergy. And we use that same idea to route things like internet traffic. But nature has another trick.
Evolution.
Genetic algorithms. You take a bunch of potential solutions, decent routes, and you breed them. You mix their properties, that's called crossover, and then you throw in a random mutation.
That mutation is so important, right? To avoid getting stuck.
Yes. It keeps you from getting stuck in what's called a local trap, a solution that seems good but isn't actually the best overall. Mutation forces the system to try something weird, just in case.
It prevents complacency. This whole idea of navigating a landscape, it brings us to modern AI, doesn't it?
It brings us right to gradient descent. Imagine you're on a misty mountain at night. That's your landscape of loss. You want to get to the valley at the bottom, the lowest error.
So you just feel the slope under your feet and you take a step down, and another, and another.
Until you can't go down anymore. That is exactly how a neural network learns. It is the ultimate graph.
Where the neurons are the nodes and the synapses are the edges, and it just keeps adjusting its own weights to step down that slope to minimize its error.
But to handle that kind of scale, You need incredible infrastructure. You can't search through that data one by one. You need things like hash tables.
Which give you that almost instant O1 access. It's like having a perfect index for the entire universe.
Right. It makes the whole thing possible.
It's just amazing that the same basic logic that guides an ant to food is now powering global logistics, medical diagnosis, and the smart cities of tomorrow.
It connects all that abstract math to the messy reality we live in.
So here's a final thought for you. If our world is just one giant complex graph and we're all moving through it, are we actually the ones choosing our path? Or are we just nodes constantly adjusting our own weights to fit some larger algorithm?
That is a deep question. It might take more than a good heuristic to solve that one.
Thanks for this deep dive. We'll see you on the next Optimize cycle.